Welcome back, Mr. Sutton here, bringing you the BC Calculus 8-6 Part 2 homework solutions on polar functions advanced area. For this problem, we want to find the area of the closed region bounded by this polar graph. So this one was or would have been a calculator question given in modern times. So let's go to the calculator for this. I'm going to start by graphing this out in polar mode so I can see what I'm looking at. So here I am on the calculator. I've got this in polar mode right here. And let's see here, I've got an interval from 0 to 2 pi in my window. Let me do zoom fit. And we see here that we're dealing with something that looks circle-ish. Let me do trace to see what my limits of integration are going to be. So we can definitely start at 0. All the answer choices do anyway. And if we do trace here to see how far around it, or how far we have to go to get all the way around, we're going through the angles from 0 to, let's see here, that brings us to pi, gives us half of this. And if we keep going all the way, we eventually get to 2 pi at the very end. So using our general formula of integral from a to b 1/2 r squared d theta, we've got an integral we could say from 0 all the way around to 2 pi, and that's going to be of just this thing right here, 1/2 times this thing squared. Now, of course, this matches none of the answer choices. We have an integral from 0 to 2 pi, but the only option is this one right here, which doesn't have the 1/2 or the squaring going on. Some of them don't have squaring, and I mean, if you square a square root, it's going to be gone. So probably one of these answer choices with a 3 plus cosine in there. And we've got this, well, there's no 1/2 either, so that's also an issue. So what happened? So this is where we need to be a little bit creative with rewriting this thing. First thing I'm going to do, I'm going to pull this 1/2 outside the integral, just because I can. And now, instead of writing this as one of these integrals from 0 to 2 pi, since this is a symmetrical shape, I could have actually just taken twice half of this thing, like gone from 0 to pi, found that area, and then doubled it. So I could rewrite this as 2 times the integral from 0 to pi. And again, that would give me the same thing. And now I could also touch this up a little bit inside. I mean, why square a square root? You can just simplify that to 3 plus cosine of theta d theta. And of course, if we just multiply the 1/2 and the 2 out here together, well, those just go away. So we end up with integral from 0 to pi of 3 plus cosine of theta, which is going to match one of the answer choices. That's going to be answer choice D. On this problem, we have this S region in the first quadrant. It's bounded above by r equals cosine of theta, and let's see here, bounded below by the graph of 2 theta. And then we intersect at this angle here of theta equals exactly actually 0.450. We want to know the area. So the key on this one, we've got our general area formula, 1/2 r squared d theta. However, this assumes that you have a single radius controlling things. In fact, from theta equals 0 until we get to this 0.450, this is all controlled by this underneath curve, this r of 2 theta. But then, after we get to that spot, now it's the cosine of theta radius strips that are giving us our area. So we're going to need to split this up into 2 integrals divided at this angle right here. So my first integral, I'm going from 0 to 0.450, and that's going to be the integral of this underneath curve, 2 theta squared, and I'll have a 1/2 in there as well. And then I'm going to have to add to that the integral from 0.450 until this looks like pi over 2 here of the other curve, so that was cosine of theta, and again, 1/2 times that squared, d theta. Let's go ahead and use the calculator for this now. So here I am on the calculator, writing out my first integral from 0 to 0.450, 1/2, and I'll call this 2x squared dx. You could go into polar mode and then it would give you thetas, but you really get the same answer here. Now let me do the second integral. So there's my integral from 0.450 to 1/2 cosine of x dx, all of which gives me a grand total of about 2.243, which is going to be answer choice B. For this problem, I have the two polar curves r equals 1 minus cosine of theta and r equals 1 plus cosine of theta intersecting in this figure and giving us some common shaded area. We want to figure out the area of this shaded part here. And this was a no calculator question, so you couldn't even really tell right off the bat which of these curves was which, unless you either kind of knew what you were doing graphing these, or you could plug in some values. So that's what I'm going to do. So in general, I've got the polar area formula, 1/2 r squared d theta, integral of that. But I need to figure out, first off, my limits of integration, and second, which function I'm actually even using. In fact, I should probably figure out the function, the r value, before I figure out the limits of integration. So I'm going to test out r equals 1 minus cosine of theta. Let me just see if I plug in a few easy angles, what I get out of this. So for example, if we plug in 0 for theta, so that would be going this way here. Well, cosine of 0 is 1. 1 minus 1 is 0. So at 0, we're right at the pole here for this function. And if we plug in, let's do pi over 2. Well, cosine of pi over 2 is 0, so 1 minus that is just going to be 1. So that brings us up here. So that's as we go from 0 all the way to pi over 2. So it's looking like this curve here is the 1 minus cosine of theta curve. But let's just do one more. Let's do r of pi. So if we do r of pi, cosine of pi is -1. 1 minus -1 is 2. So that brings us out here, 2 away from the origin at a value of pi of 180 degrees. So definitely is this lefty kind of cardioid here. All right, so now we know what the r is going to be, or at least one of them. Now, how do we actually get the shaded region out of that? Well, my strategy on this, I've got these two teardrop shapes here. They're both the same area. And in fact, they're both, you can split them up into halves. So if I just found the area of this little half here in the first quadrant and multiplied that by 4, I would get the area of all this shaded stuff. So I'm going to do that now. So there's my curve that I'm going to be using for my r value. So let me do 4 times the integral from, this is going to be 0 to pi over 2. And again, that's going to be the 1 minus cosine curve here. So half of that squared, d theta. And let me see if that matches one of my answer choices. So looking at my answer choices here, I've got a 1 minus cosine squared only in choice C. And that's going from 0 to pi over 2, just like ours. And it's got a 2 out front. Well, 4 times 1/2 is 2. So that's definitely going to match choice C. And we're done. On this problem, we want to know which of the following equals the area of the region inside the polar curve r equals 2 cosine of theta and outside the curve r equals cosine of theta. So if we look up at this picture here, inside the 2 cosine theta, so that's going to be inside this big circle, but we want to be outside the small circle. So we basically want to do big circle minus small circle and match one of these answer choices. Now, it's usually a good idea to use symmetry to help us out. So our strategy on this, rather than finding the total area of this circle, because maybe it's hard to know what our limits of integration should actually be, maybe we're going around twice and don't even know it, no calculator question, hard to tell, our strategy is going to be to subtract the small circle from the big circle just in quadrant 1. And then multiply whatever that is by 2, and that'll definitely give us this total area. All right, so quadrant 1, and we're multiplying by 2. So my area is going to be 2 times, and now I'm going to open a big old parentheses. I'm going to need the integral from 0 to, let's see, this will be pi over 2. Just of the big circle initially, so 1/2, and then in parentheses 2 cosine of theta squared, d theta, plus, or minus rather, I'm going to subtract the small circle now, pretty much the same idea, integral from 0 to 1/2 of, and I'll have 1/2 cosine squared theta. Now because I have the same limits of integration, if I really wanted to, I could put these in the same parentheses, and I could pull out this 1/2 and do a bunch of other algebraic trickery here. But let me just take things as they are and try to simplify this, because we do have to simplify this. None of the answer choices match. So let's keep going. So in here, I can definitely square all of this. I mean, if you look at the answer choices, a lot of them have a cosine squared in them. So that seems to be what they want us to do. 2 cosine squared, that's going to be 4 cosine squared theta, times a 1/2 is going to bring us back to 2 cosine squared of theta. But then we distribute this 2 out here. So this first integral here, grand total of 4, integral from 0 to pi over 2 cosine squared of theta d theta. Now this next one, well, if I square all this, I've got 1/2 cosine squared. But then I'm going to multiply that by the 2 out there, so that's going to be 1 of those cosine squared integrals. So I've got 4 of this integral minus 1 of the same integral, basically. Well, just combining like terms, that's going to be 3 of those integrals. So that's going to be, let's see here, which answer choice? We need a square in there, so that looks like answer choice A. On this problem, we've got this cute-looking graph here of a circle with some petals inside, and we want the sum of the areas of the shaded parts here. All right, so this is one of those where if I were not allowed to use a calculator, I would figure out the area of just one of these petals or even a half petal and then multiply that by a certain number and subtract all of that from the area of the circle. But since I'm allowed to use the calculator, let me plug all this in the calculator and see what I can do with it. So there are my 2 curves, the circle 2 and 2 cosine of 3 theta, which is going to give me those petals. Let me do zoom 0 now. And I've got my window set from 0 to 2 pi, going by increments of pi over 36. Otherwise, it looks kind of choppy when you graph those petals if your increments aren't fine enough. So there we go. It's the same picture they gave us. Now, what I'm really interested in, I mean, I know how to take the area of a circle even without calculus. We can just use pi r squared for the circle and then subtract the petals. So that's our general strategy, circle area minus petals. But how about the area of those petals? So again, if I weren't allowed to use a calculator, I would probably just find like this little half petal in quadrant 1 and multiply it by 6. But since I am allowed to use the calculator, let me trace my petals and see how far I have to go to get just the area of all of them at once. So going to trace, and if you look in the upper left, it tells you which function we're on. I'm going to press the down arrow to get my trace little spider here on the second one, the 2 cosine of 3 theta. And as I move around here now, I'm tracing through these petals. And let's see here, this is going to be the quadrant 3, the quadrant 2 petal, and we come all the way back around to the beginning. And how many degrees or radians did we need to do that? We went from 0 to, this is pi radians right here. So we actually complete 1 full cycle on the interval from 0 to pi, which is good to know, because if you went 0 to 2 pi, you'd be double counting all those petals. So what I'm going to do then, I'm going to use a little geometry for the circle area. So that's going to be, we have a radius of 2, they told us. That's going to be pi times 2 squared for my circle. And now from that, I'm going to subtract an integral from 0 to pi of, well, this stuff right here, 1/2 this stuff squared, d theta, because we had the 1/2 from the original formula. All right, so let me plug all this in the calculator. So here's what I've entered in my calculator. I have the pi times 2 squared minus integral, so this was math 9, 0 to pi. I did a fancy fraction here for 1/2. And then for all of this stuff, I actually entered this in R2 when I graphed it out. So I'm going to do R2 and then just square that. It's a little bit easier to deal with. D theta, enter, and that comes out to 9.425. So that's choice D. On this free response problem, we have these graphs of r equals 4 and r equals 3 plus 2 cosine of theta shown above. And they're telling us that these intersect at pi over 3 and 5 pi over 3. And that was just decent of them to tell us this, because this is a no calculator question, so it's kind of annoying to have to solve that on our own. But they gave it to us. Okay, so R is our shaded region. and it's inside r equals 4, outside 3 plus 2 cosine of theta. We want to have an expression involving an integral for the area of r. So we don't actually have to find the area, but we do need to set up an integral to solve that problem. So my basic strategy here, we basically want to take the circle, the r equals 4, from this spot right here, this pi over 3 angle, all the way down here to 5 pi over 3. We want to take that and just subtract the cardioid on the same interval. So I have all of these distance strips from here to here for the circle, and I just want to chop out the little radius strips along the cardioid for that. So I'm going to have an integral of, this is going to be, let's see, from pi over 3 to 5 pi over 3. Let me just also label my r functions here. So I'm going to call r equals 4 r sub a of theta, and I'm going to call this other one r sub b, just so I can quickly refer to them for the rest of this free response problem without having to write them over again. Maybe it was a little overkill with this 4, but this at least tells people exactly where I'm getting the number 4 from, instead of just like sticking 4 in there and saying, hey, it's 4. Now we know that this is the radius function for one of these polar curves. So I have an integral from pi over 3 to 5 pi over 3, and I've got my circle now, so this is going to be 1/2 times RA squared d theta, and then I'm going to be subtracting the integral along the same interval there, same limits of integration, but now I'm subtracting this other function in here, so 1/2 r sub b squared d theta. And this will do it. We've told them what these things really mean. We're taking one area, subtracting the area inside. We've set up an integral. On to the next. For this problem part, we want the slope of the line tangent to r equals 3 plus 2 cosine of theta at pi over 2. So basically finding the slope right here on this cardioid. We can see right away just by looking at the picture it's a positive slope and not super steep, probably less than 1. But let's actually find the exact value of this. So to find slope, which involves an x versus a y, we need to express this r function parametrically in terms of x and y. So I'm going to start by writing x of theta, a formula for that. Now in general, your x value is just going to be the r times the cosine of theta. Here I'm going to write r sub b of theta, cosine of theta, because it's this r, not the other r. If you just write r, it's like, well, which one do you mean? So actually, multiplying this out, I'm going to distribute this here. So I've got cosine times 3, so 3 cosine of theta, and also cosine times 2 cosine of theta, so 2 cosine squared theta. And I always like to distribute these. I've found more often than not, when I have to take the derivative, it's easier if it's just expressed in terms of terms instead of a product, because I don't feel like doing the product rule unless I really have to on these. So let's go ahead and take that derivative now. Not really much to do to simplify it before we do x prime. So that's going to be negative 3 sine of theta. And then this next one, using the chain rule, I've got 4 cosine of theta times the derivative of cosine, which is negative sine of theta. This I can clean up a little bit. Eventually I'm going to have to plug in pi over 2, so the fewer places I have to do that, the better. So I've got negative 3 sine of theta, and then this stuff here, well, 2 sine of theta cosine of theta is equivalent to sine of 2 theta. It's that double angle identity. So I can call this negative 2 sine of 2 theta. All right, so let's move on now to expressing y of theta. That's going to be r sub b of theta times sine of theta, which if I distribute that, I end up with 3 sine of theta, and this is 2 sine cosine. Cleaning this up a little bit before I take the derivative, because otherwise I need a product rule here. This second term, I can convert that to just being sine of 2 theta. Again, using that double angle identity that I used right here before. Only this time I'm using the double angle identity before I take the derivative instead of after. So taking our derivative, 3 sine of theta is going to become 3 cosine of theta. And then this next term, now I avoid taking a product rule. Now it's just a simple chain rule. This is going to be 2 cosine of 2 theta. All right. In general, dy over dx evaluated at pi over 2. That's going to be y prime of pi over 2 over x prime of pi over 2, just using our parametric slope setup here. So that's going to be pi over 2 plugged into this y prime. So 3 cosine of pi over 2 plus 2 cosine of 2 times pi over 2, all that. And now we've got pi over 2 plugged into the x prime right here. Let's go through now and evaluate this. Actually, we don't have to evaluate it because these are all technically considered constants. So if you stopped right here, you would actually be good. You really have nothing to gain by moving on other than feeling good about yourself and your ability to simplify trig functions. But I want that feeling, so we're going to keep going here. But this is one of those don't try this on the actual test sort of deals. So we've got cosine of pi over 2. That's really 0. Zero's out this whole term. Over here, 2 times pi over 2. That cancels, leaving us with a pi. Cosine of pi is negative 1. 2 times that is negative 2. So we have 0 minus 2, or just negative 2 in the numerator when all is said and done. Downstairs, well, sine of pi over 2 is 1, so this is really negative 3 for that first term. Over here we've got sine of pi, which is 0, so negative 3 is all that's left down there. And of course you could go a little further and call this 2/3, which is kind of realistic based off of what this picture looks like in terms of the slope of a tangent line right there. On this last problem part, we have a particle moving along the 3 plus 2 cosine of theta curve between 0 and pi over 2. And it's such a way, so it's moving between, let's say, it's this spot right here. Okay, in the first quadrant. So it's moving in such a way that the distance between the particle and the origin increases at a constant rate of 3 units per second. They want the rate at which our angle is changing with respect to time when the position is pi over 3. So we've got one rate of change, we've got kind of an instant value, we're looking for another rate of change. This is one of those where you have to say to yourself, this is a related rates kind of problem. If we're doing a related rates kind of problem, it means at some point we need to implicitly differentiate some equation that ties everything together. So what equation should we use? Well, they kind of gave it to us right up here. The curve r equals 3 plus 2 cosine of theta. And the only thing you have to be careful about with these polar problems is, do I use the original curve, or do I have to express this parametrically and talk about it in terms of x and y? So taking a look at the rate of change that they're giving us here, they said the distance between the particle and the origin. Well, that is represented by r. That is what r really means when you get down to it on the graph. So we can use this original. We're just going to implicitly differentiate this r they gave us right here. So going from left to right, the derivative with respect to time now, of r, is dr over dt. So anything that's not a t is considered an inner function at this point, and we need the chain rule. 3 gets differentiated away to 0. This next term, 2 cosine of theta, well, the derivative of that is going to be negative 2 sine of theta. But now theta is not t, so it's an inner function and needs the chain rule. So we'll multiply this by a d theta over dt chain tail here. All right, so we've got our derivative that ties everything together. Now we basically plug in everything we have and solve for the stuff we don't have. At the end of the day, we want the rate at which the angle is changing with respect to time. So we're trying to solve for d theta over dt. That means I better have something to plug in for dr over dt and theta. Well, dr over dt, that's the rate at which the particle's distance from the origin is changing. They gave us that. They said that that was increasing at a constant rate of 3. So we're going to plug in positive 3 for dr over dt. And now the theta itself, well, they said when the position of the particle corresponds to theta or pi over 3. So theta is pi over 3 then. So we have negative 2 sine of pi over 3, all of that times d theta over dt. What is the sine of pi over 3? I mean, you don't actually need to know it. You could just write d theta over dt equals 3 over negative 2 sine of pi over 3. And since it's all constants, then you would be good. But sine of pi over 3, that's really, this is really 60 degrees, so that's going to be radical 3 over 2. And now the 2 here and the 2 down here cancel, so this is really negative radical 3. I can divide both sides by negative root 3. So d theta over dt equals negative 3 over root 3. And if I want to be really crazy and simplify the radical, this is, let's see here, multiply by root 3 over itself. So negative 3 root 3 over 3. 3's cancel. We just have negative root 3. So this is the most simplified version of the final answer. But again, if you wrote 3 over really all this sine stuff, you would have been good. Now we do need to have units of measure on this one. So let's see here. They said find the rate at which the angle changes with respect to time. Well, what units is our angle in? Our angle is always in radians. We never use degrees in calculus. So radians it is. And with respect to time, well, what time units are we dealing with? Just looking at some of these other rates of change, our dr over dt was expressed in terms of units per second. So second is our time here. So that means then we have to have radians per second for the units on this one.